Let's go ahead and review electron configurations and then apply what we've learned about quantum numbers to electron configurations. All right, so when we look at electron configurations, this should hopefully be a review from Prep Chem. So there is a filling order. What we're going to do is we're going to fill the lowest energy orbitals first and then continue to higher energy orbitals. Okay, now if you recall, what's going on is we start with the lowest, which is our 1s, and then we move to 2s, and then 2p, and then 3s, and then 3p, and then 4s, and then to 3d. Okay, so we get degeneracy in the orbitals. There's things that happen within an atom that cause these energy levels to split. And so a consequence of that is, interestingly enough, the 4s orbitals are actually at a lower energy than the 3d. Okay, all right, we can only put 2 electrons in each orbital. We've got the different spins, so we get our spin up, we get our spin down. And then when we fill our sublevels, we start with a single electron, and then we go back and spin pair. Okay, this is based on Hund's rule, which is that we pair only after each orbital in a subshell is occupied by a single electron. And so, you know, if I've got, let's say my 2p electron or orbitals, and I have 4 2p, I would do 1, 2, 3, and then I would go back and spin pair for the 4th there. Okay. All right. And so when I look at my orbitals here, I've got hydrogen, and then I've got multi-electron atoms. Okay. As soon as I go from hydrogen to helium, I'm in a multi-electron atom. So my multi-electron atoms are everything else. That's a really funky looking G. And I do mean everything else. So there's hydrogen, and then there's the rest of the periodic table. Now, so hydrogen's easy. All the sublevels of our quantum levels are each the same energy. Okay, that's why you see the straight lines for 2p, 3s, 3p, 3d, 4s, etc. Now, as soon as I increase the number of electrons in my sublevels, these sublevels become degenerate. All right, they change in energy, so we see degeneracy. Okay, so we get degeneracy in that sublevel energy. As soon as I have more than one electron, now my electrons have an effect on each other. Okay, each additional electron is going to change the Z effective nuclear charge. So we get this Z effective. This is our effective nuclear charge. And all that is it's basically the amount of charge any given electron feels coming from the nucleus. So remember that our nucleus is where all our positive charge is from. Okay? When I have something like hydrogen, the only things interacting here are that one electron and the nucleus. Now, as soon as I move from hydrogen to helium, I'm in the same energy. I'm in the same sublevel and everything. So I'm going to put that electron in there. But now things get more complicated. Now those two are going to interact with each other. And then that's also going to interact. And so each additional electron means each electron may feel more or less effective nuclear charge. And will have different energy levels based on that kind of sublevel it resides in. As soon as I've added that other electron in, now I've complicated things. Now I've caused things to start to split because now instead of it just being a simple interaction between the electron and the nucleus, now I have interactions between the electrons themselves and the nucleus. Okay? It can get even more complicated. Let's say now I'm moving out to another energy level. Add that electron in there. Now I'm going to get interactions here, and then I can get an interaction there. So now I'm getting buffered from all that charge, and I'm shielded from it from those inner electrons. And so we get all this crazy stuff happening. My s orbitals, those are going to have the greater probability of residing close to the nucleus, so those are lower in energy. All right, and so my atomic orbitals of a multi-electron atom do resemble those of hydrogen, but because of adding another electron in, now I have interactions with my electrons, and I wind up with that degeneracy. I start to see more spectral lines, which are consistent with energy split into those sublevels. Okay? All right, so we have our filling order. Periodic table goes along with this super well. I've got, group 1A and group 2A. Those are my s electrons because I can only have 2 of them. Then I go across the periodic table to the rest of the main group. Okay, boron through, the end. If I can't across, there's 6. Well, guess what? 3 p orbitals. I can put 6 electrons in. If I can't across my transition metals, there's 10. There's 5 d orbitals. Can take 10 electrons. Lanthanides and actinides, there's 14. There's 7 f orbitals. I can fit 14 electrons. Hopefully this is all review from your prop chem class. Okay, and then you can see things like this. Some people like this diagram, some people don't. You just got to know that filling order. All right, and so we can take our electron configurations. We can write out the configuration. We can do an orbital diagram. So this would be my 1s. Okay, so helium, I've got 1s2. 1 spin up, 1 spin down. Carbon, now I'm going to go out to, 2s2, 2p2. Now, if I look on my periodic table, so I can look behind me, let's see here, helium ends period 1, okay? So I can also write this in a shorthand like this. All right? So these are my valence. And this is my core. And so I can use a shorthand or a noble gas configuration in order to make sure that I'm accounting for everything that was in helium. Early on in the periodic table, it's not so big a deal, but when we get later on and electron configurations get really long, it's nice to be able to write those shorthands. Okay, and so I can keep filling. So let's practice a few here. So I would like you to try sodium, vanadium, chromium, nickel, and copper. Okay, those are all down there. We've got sodium, which is in period 3, and then the others are in period 4. Okay, see if you can remember how to write electron configurations. Now, a couple of these are going to be unusual ones. All right, so pause and see how you do. All right, let's see how you did. So sodium, neon, 3s1. Vanadium, argon, 4s2, 3d3. Okay, now chromium is an exception to the rule. Chromium is going to look like this: argon, 4s1, 3d5. Okay, in period 4, there's 2 elements that have electron configurations that are exceptions. You just have to know these. Now in period 5 and beyond, there's a lot more exceptions. Okay, so if I want you to know one, I will let you know you need to know this. You do need to know chromium and copper. They are exceptions to the rule. You got to know them. The other ones, I'm not going to make you memorize every single exception on the periodic table. I might say, what is the expected electron configuration for, an element? Or we can use things like magnetic properties, which we'll talk about in a little bit, to help us predict what we might see insofar as a particular element's configuration goes. Okay, but you do need to know chromium and copper. Okay, those are the 2 exceptions. So nickel is argon, 4s2, 3d8, and then copper is our other exception, argon, 4s1, 3d10. Okay, it's energetically more favorable to leave that single electron in S than to have an unpaired electron in D, or for chromium, it's more energetically favorable to have single electrons in all of those. Okay, and so we can start to look at our orbital occupancy. All right, and so here, you can see, here's my chromium, Here's my copper with their exceptions. And then when I look down to period 4, I start to see exceptions starting at element 41. Tons of exceptions all over the place, all right? And so, again, I'm not going to make you memorize every single exception on the periodic table, but, and then there's a whole bunch more in the lanthanides and the actinides as well. But you do need to know chromium and copper. Those I will expect. And we're going to look at, like I said, some ways you can predict what you see based on magnetic behavior. Okay? All right, so then we have this thing called the Pauli exclusion principle, and this is going to let us relate things back to those quantum numbers. All right, so we cannot have the same set of quantum numbers for 2 electrons. Every electron must have its own unique set of quantum numbers. All right, we've got the first 3 quantum numbers are defining the orbital, and so then we have to make our unique set with the spin. So remember, we have our N, our L, our M sub L, and our M sub S. So these are going to define the orbital. And then that N sub S is going to be the spin quantum number. And so we can have the same N, L, and M sub L, but then our M sub S is where we're going to differ. And so each electron must have a unique identity okay, as expressed by its set of quantum numbers. Okay? All right, and so let's recap here. So remember, we have our principal quantum number. That's going to let us know what energy level we're at, 1, 2, 3, 4. Angular momentum, so that's 0 to n minus 1. Our magnetic, negative L to plus L. And then our spin is just, are we spin up or are we spin down? Okay, so let's take a look here. All right, so let's look at helium. Okay. Helium, we just have a 1s2. All right. So there's my 1s. Okay. Now, for an s orbital, I have an L of 0, so the only M sub L I could have is 0. All right, so I'm going to number this electron 1. I'm going to number this electron 2. All right, and let's just write some quantum numbers and see if we can get a unique set of quantum numbers for both those electrons. So electron 1. So N is going to be 1. L, it's an s orbital, so my L is 0. My M sub L is also 0. It's pointing upwards, so my M sub S is positive 1/2. Okay, for electron number 2. Okay, my N is still 1. My L is still 0. My M sub L is also still 0. But now my M sub S, it's pointing down, so it's negative 1/2. So each electron has its own unique set of quantum numbers. Okay, let's look at carbon. Again, that's 1s2, 2s2, 2p2. So we're going to get our 1s, our 2s, and our 2p. Okay, all right, so let's take a look at carbon's p electrons. All right, so let's number these. So I have electrons 1 and 2, 3, then 4, electron 5, and electron 6. Okay, so let's define some M sub L's. So 0, 0, and then we'll get negative 1, 0, and positive 1. All right, so for electron 5, let's see if we can get unique numbers for each of these. Okay, electron 5, my N, it's in a 2p, so my N is 2. It's a p, so my L is 1. My m sub L, according to the way I wrote that there, is -1. We just go across, all right? You just go from negative L to positive L through 0. You just go from left to right, do it across. And then it's pointing up, so my m sub S is +1/2. Okay? All right, and then electron 6, similar deal here. Okay? So we still have an N of 2 because we're still in a 2p. We still have an L of 1 because we're in that p. Now my m sub L, it sits in the one that I identified as 0. And my m sub S is still +1/2. So did we get unique quantum numbers there? We did. Okay, so let's take a look at this one. We're going to look at fluorine. We're going to write quantum numbers for the 8th and the 3rd electrons of fluorine. Okay, so I'll start you off. All right, we're going to get that 1s2, 2s2, 2p5. So 1s, 2s, 2p. Okay, so try those. See if you can do those. All right, let's see how you did. So we'll go ahead and put our electrons in. All right, so we've got electron 1 and 2, 3 and 4, 5, 6, 7, 8, and 9. Okay, so I asked you to do 3 and 8. So we'll color code 3 here, and we'll color code, oops, 8 here. Okay, we'll do our m sub L's. Okay. All right, so for 3, we're going to n equals 2, L equals 0, m sub L equals 0, m sub S equals +1/2. Okay, and for 8, you should have gotten n equals 2, L equals 1, m sub L equals -1, and m sub S equals -1/2. Okay, try one more. Let's see here. Try to do 7. Okay. All right, how did you do? So for 7, you'll get an n equals 2, an L equals 1, an m sub L equals +1, and an m sub S that equals +1/2. Okay? All right. Now I want you to try silicon. Okay? So pause, see if you can write out the electron configuration and fill in the orbital diagram for silicon first. All right, let's see if you got that much. So silicon, we're going to get 1s2, 2s2, 2p6, 3s2, 3p2. We're going to get 1s, 2s, 2p, 3s, 3p. Okay. Okay, and we can number our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. All right, so let's see here. Let's have you do number 7 and number 13. Okay, so pause and see if you can do some quantum numbers for 7 and 13. All right, let's see how you did. First of all, we got to get our m sub L's in. Okay, so 7. We're going to get n equals 2, L equals 1, m sub L equals positive 1, m sub S equals positive 1/2. Now, think about what we just did for fluorine. Is this the same set of quantum numbers that electron number 7 in fluorine has? It should be, because we fill in the same order. And so it doesn't matter where you're at on the periodic table, electron 7 is always going to have the exact same set of quantum numbers. Now, we do start getting into some exceptions to the filling rule when we get up to chromium, but chromium is atomic number 24. So we don't start seeing any deviations in our quantum number set for any given electron until we get into the 20-somethings for electrons. So it doesn't matter where you're at the periodic table. Electron 7 is always going to fill at the same point and is always going to have the exact same set of quantum numbers. All right, and then to finish off 13, you should get an n equals 3, an L equals 1, an m sub L equals -1, and an m sub S equals positive 1/2. All right, so this is how we're able to tie in our electron configurations and all of our quantum numbers.